discussion. So last week we concluded the third week of the course, where we started the discussion on aggregate characteristics by talking about packing density of aggregate in a single sized and multi-site system. We derived how void percent of a binary aggregate system will depend upon the aggregate proportioning. Then we saw its relationship with, with packing density, and we solved a couple of numericals to understand the application of this concept. We then talked about aggregate grading, where we saw IS 383 grading charts. In this slide, you can see table 2 of IS 383, that is for coarse aggregates that we discussed. Similarly, we discussed grading charts for fine aggregates and all in aggregates that are present in IS 383. For characterization of aggregates based on gradation, we talked about fineness and surface modulus, and we solved one bin numerical for each. Then we talked about properties of aggregate, wherein we saw physical properties like specific gravity and water absorption, mechanical properties like crushing value, impact value, and abrasion value. And we just had an overview of chemical properties like alkali aggregate reaction and soundness. And in the final segment of last week discussion, we talked about chemical admixtures. We introduced what chemical admixtures are and different classification of chemical admixtures, like chemicals interacting with the hydration, interacting in hydrations, which are accelerator and retarders. Those who adsorb on the chemical cement surface for better particle dispersion, like plasticizers and superplasticizer. Those who affect the surface tension of water, which are air entrainment admixtures. Those who affect the rheology of water are viscosity modifier, and some special chemicals which act on the hardened concrete like corrosion inhibitors and water repellent. Now, we discussed in detail about dispersion admixtures, which includes plasticizers and superplasticizers. We talked about their action, application, and basic chemistry behind their action. We saw the end result of plasticizers in modifying a concrete mixture, either for maintaining the same property of compressive strength and workability, but with reduced water content and cement content, or with increased strength with reduced water or increased workability by keeping the same W by C ratio with the addition of SP. After this, we talked about the action, application, and basic chemistry behind working of set controlling admixtures, which includes accelerators and retarders. And finally, we talked about some other special purpose admixtures like air entraining admixtures and viscosity modifying admixtures. We also touched a little bit on waterproofing agents, shrinkage reducing admixture, and alkali silica reaction reducing admixtures. So, this was all that we discussed in the last week content. Now, last week there was one question that was posted, which for which the solution was needed. So first, we'll just quickly see the solution to this question first, and then we'll start with the content ahead. Okay, so this was the question. A cement paste was prepared with 300 gram cement and a water to cement ratio of 0.3, and we are asked to calculate the volume of gel pores in centimeter cube at the end of 1 year, assuming maximum hydration has taken place in 1 year. So I will just tell you how to solve this question. Okay, so step one is to write whatever values is known to us. So we know the mass of cement is equal to 300 grams. Density of cement we'll assume as 3.15. Mass of water will be, that is there initially, is zero point 0.3. WSE ratio is zero point 0.3. So zero point 0.3 times 300 will be 90 grams. Density of water is equal to 1. This is specific gravity. Okay, sorry. I should have said. Okay, you can understand as 3.15 gram per centimeter cube. You can write here density, and here I will write 1 gram per centimeter cube for water. Then We have given maximum hydration we need to assume. So degree of hydration I will assume as 100%. Okay. Though an actual condition 100% may not be possible in any in any binder combination, but right now we are assuming 100%. And density of cement paste I am taking as 2.51. Okay. So step 1 will be to calculate the volume of hydrated cement. So volume of hydrated cement will be, how I can calculate, I need to assume that 23% water is required for complete hydration. Okay, this I am assuming. And this we have already derived when we talked about chemically bound water, and we saw it is like 23% water is actually required for complete hydration. That calculation we saw. Okay, so if I assume this, then my volume of hydrated product will be nothing but 1 plus 0.23 times 300 divided by 2.15. Okay, so this value will come out to be 147.01 centimeter cube. Okay, so this is the volume of my hydrated product, and I can write the volume of initial assembly also, like where cement and water are separated. So that will be nothing but 300 divided by 3.15 plus 90 divided by 1. Okay, so this is my unhydrated volume of my system. So that is 185.24. Okay, now step 3 will be the calculation of gel porosity. So we know gel porosity, suppose I am writing it as Wg, is 28% of total hydrated product. Okay, this we know. Okay, so my total hydrated product I can write as my actual hydrated products that know of volume of which I know, and plus gel pour. Okay, so 28% of this total hydrated product volume is my gel porosity. So what I can write, gel porosity Wg, either here I also write Wg upon total hydrated product volume, that is hydrated product plus Wg is equal to 0.28. Okay, so I know this value I have already calculated, which is 147.01. So upon solving, you will get Wg is equal to 57.17 centimeter cube. So this is my gel porosity, which was asked in the question. You can also go one step ahead if you want to calculate the capillary porosity volume. So capillary porosity volume will be nothing but initial volume of my system, which is 185.24, minus final hydrated volume of my system, which is 147.01. So that will come out to be 38.23. Okay, so this is how we solve the question. So gel porosity is 57.17 and capillary porosity is 38.23. Okay, so in the question we are asked gel porosity, so the answer will be 57.17 centimeter cube. Any doubt in this solution? To who asked me this question, I don't remember. Okay, I guess this question is from week 2 assignment. So the answer will be 57.17. They usually answer in like range like 50 to 55, 55 to 60. So you may your correct answer will be like, if it is close to 57.17 also, it will be correct. Okay, so now let's move ahead. So in week 4 content, we were introduced to mineral admixtures used in concrete. Okay. Now, what are mineral admixtures? So if I go along with the basic definition of admixture as per IS 9103 guidelines, it says that a material other than water, aggregates, or hydraulic cement which is used as an ingredient in concrete or mortar and added to the batch immediately before or during mixing to modify one or more properties of concrete in a plastic or hardened state is known as admixture. Okay, so any admixture is any material which is added before or during mixing to modify the property of concrete in plastic state or hardened state. Plastic state means fresh state. Okay, in fresh state, my concrete is a plastic material. It can deform. Okay, now we know that admixtures are further classified into two types. There is chemical admixture and there is mineral admixtures. We have already discussed about chemical admixtures. So what are mineral admixtures? So these are finely divided siliceous materials which are generally powdered material which are added to concrete to improve its property. So these are like basic definition of a mineral admixture. They are also known as supplementary cementitious material since they are added as a partial replacement of OPC for maintaining or enhancing the properties of concrete. Okay. Now, why we are using mineral admixtures? What are the benefits of using mineral admixture? So, first point is they promote sustainability in terms of cost and energy saving. How? Because we are using them as a partial replacement of Portland cement. We know cement is expensive, it requires a lot of energy and it generates a lot of CO2. So instead of cement, when we use a SCM, which are basically derived from waste or unwanted residue material, they reduce both cost and energy and they help us to practice a sustainable construction. Okay. Now, second benefit of using SCM is they can improve the strength and durability of concrete. How? By reducing the water demand, by improving the rheological behavior, by making concrete rest permeable, or by acting as a filler. So there can be various ways in which they can improve the strength or and durability of concrete that we'll discuss in today's session. Now, how these SCMs are produced. So, a couple of weeks ago, we had a very brief overview on the source of production of few SCMs. So, let's see today a little bit in detail about them. So, most commonly used SCMs are fly ash, ground granulated blast furnace slag, and silica fume. So, our discussion for today will be on these three SCMs only. So, first is the production of fly ash. So basically, fly ash is a fine particulate residual which are obtained from pulverization of coal burning, which is primarily obtained from coal-based electrical generation plants. Okay, so they are also known as pulverized fly ash. Okay, so now how they are produced in this coal burning process? So what happens? First, my coal is pulverized into fine powder. Okay, and they are burned in a boiler to produce heat for generating electricity. Okay, so here my coal is burned to produce heat. Now, during this combustion, what happens? Inorganic materials that are there in coal, like silica, alumina, iron, and calcium, they do not burn. Instead, they become a molten ash. Okay, so here we will have a molten ash. Okay, now, after combustion, this molten ash is carried upward with the hot flue gases. Okay, so gases which are coming out of the flame, they carry these molten ash. And as these gases move away from this high temperature zone, during combustion, they cool down. So, as these gases move upward, they cool down. Okay, and with them, my ash also cools down in the upper section of the boiler. Now, when these ash particle is exposed to this cold environment, they solidify into fine glassy and spherical particles, which is what is known as fly ash. Okay. Now, the flue gas and the fly ash, they are then from flue gas, I will separate out fly ash. using electrostatic precipitator, or we can say baghouse filters. Okay, before this gas is released into the atmosphere. And apart from these ashes which are moving upward, there are heavier and non-airborne particles also during the coal combustion, which settle at the bottom of the boiler, which is known as bottom ash. Okay, so there's bottom ash and there's fly ash. Fly ash are lighter particles which move upward with flue gases, and bottom ash are heavier particles which settle down during combustion. Okay, now I have separated the fly ash from the flue gases, and I have so this captured fly ash, they are either stored in the silos, which is used later on in construction work, like mainly in cement and concrete industry, or these fly ash particles are disposed of in ash ponds or landfill if not used. Okay, now the nature of fly ash that I am obtaining here in silos, it depends upon the coal that I am burning, the properties of coal. Okay, how? We have two types of fly ash. Okay, if my coal is bituminous or anthracite coal, I will have class F fly ash, which has low calcium content. Okay, however, if my coal that I am burning is lignite or subbituminous coal, it has a higher calcium content, so I will have class C fly ash. Okay, so depending upon the coal which I am burning, my classification of fly ash that I has produced can change. And this is how fly ash looks. It is like gray powdery substance that we obtain at the end. Okay, that we collect here in the silos. Now after fly ash, we have ground granulated blast furnace slag. So ground granulated blast furnace slag is obtained by quenching molten iron slag from a blast furnace in water or steam. So in simple term, it is a byproduct of steel making process, especially from the production of iron in a blast furnace. So how it is produced? So during iron production in a blast furnace, you can see here we have a blast furnace in which steel making or process take place. I have iron ore, I have coke, and I have limestone, which is fed into the blast furnace. Okay, here what is the role of coke? So coke act as a fuel and a reducing agent, while limestone is helps it is used to improve impurities from the iron ore. Okay, now there is a very high temperature inside this blast furnace, up to 1500 degrees Celsius. So what happens at high temperature of this range, the iron ore is reduced into molten iron, and the impurities that are present in the iron ore, they form a molten slag which floats on the top of my molten iron. So this is my molten iron and this is my molten slag. So from here I am feeding all the raw materials, they are heating, and my molten iron will settle down and molten slag will float at the top of my molten iron. Now this molten slag, it is separated from the molten iron, and to produce granulated blast furnace slag, the molten slag is rapidly cooled by quenching with high pressure water, or you can say air quenching also can be done. And this rapid cooling, this rapid cooling is what is known as granulation, and this is done to prevent crystallization and from a glassy granular material, what is known as granulated blast furnace slag. Okay. Now, once I have obtained this granulated slag, I will dry the slag to remove any kind of moisture. And after drying, this slag is ground in a ball mill to a desired particle size, which results in ground granulated blast furnace slag, which is like off white or white in color. Okay, so this is how my ground granulated blast furnace slag is produced. So first in iron ore, I have coke and limestone. Okay, burning, I will get molten slag. Molten slag, I will send for rapid quenching, which is also known as granulation. My granulated particle, I will allow them to cool down so that all the moisture has been removed, and then it will be ground to a suitable size, which is known as ground granulated blast furnace slag. Next, we have the production of silica fume. So, primary raw material for the production of silica fume is quartz, coke, coal and wood chips. Okay, so first of all, what is silica fume? Silica fume, or is also known as microsilica, and is it a byproduct of production of ferrosilicon alloys or silicon metal in an electrical arc furnace? So silica fume is produced in a electric arc furnace. So primary material is quartz, okay, and they have some carbon sources like coal, coke, and wood chips also. These material are fed into a electric arc furnace to produce silicon and ferrosilicon alloys. Okay, inside the furnace, the temperature is around 2000 degrees Celsius, and where chemical reaction occurs. Okay, so my silicon, it is like it will convert into a silicon metal. Okay, this quartz, it will convert into silicon metal. Okay, now the silicon metal and the ferrosilicon alloy, it is collected at the bottom of the furnace. However, during the process, silicon monoxide is also produced, SiO gas. It is produced and it rises with the hot gases. Okay, when this SiO gas reacts with oxygen in the cooler part of the furnace, it again oxidizes back to SiO2. Okay, so initially I had SiO2 only. Okay, which I converted to produce silicon metal and SiO. But this SiO gas, it again rises and it reacts with oxygen to form SiO2. Okay, this exhaust gas is then collected into a Baghouse filter, and which is where fine silica fume particles are captured. Okay, so this SiO2, these are fine silica fume particles which are captured in the Baghouse filter. Okay, and this is how we produced silica fume. Okay, so again, it is a residue of a uh, power from a metal producing industry. Okay, now this produced silica fume, they can be collected as densified material or can be left as very original material. Okay, why there are two types, densified and original? Because they are very fine product. Okay, so they, you can see here they have two images as in powder. This is how silica fume is collected, or there can be densified silica fume also. Okay, one third form of silica fume is slurry, where 50% water I have, and I have 47% silica fume and 3% chemical agent. Okay, so this is also how I can collect the silica fume, so that I can keep the silica fume in suspension and prevent them from gelling. So this is how three types of silica fume we can produce, we can collect from a silicon metal producing industry. Okay, so this is how my three basic mineral admixtures are produced. Fly ash is produced from burning of coal. Ground granulated blast furnace slag is produced from quenching of molten iron slag. Okay, and third is silica fume, which is produced from burning of silicon metal. Okay, the production of silicon metal. Now comes the important part. These produced SCMs, why they are like reactive in nature. Okay, so the SCMs that we have produced, they are also known as pozzolans. Okay, pozzolana or pozzolan, and they all have amorphous nature. Okay, that was imparted to them during rapid cooling or grinding process, and that's why they have the ability to replace a certain portion of OPC and what is known as pozzolanic reaction. So in this slide you can see a pozzolan refers to a class of silica or aluminous material which on their own don't have any cementitious property. However, in finely divided or in the presence of moisture, they can react with calcium hydroxide, which is released during Portland cement to form cementitious properties, compounds having cementitious property. So these pozzolan, they are just amorphous silica and alumina that we have produced during the that was produced as raw material during the metal industry. They themselves, they can't react with the water, but in the presence of calcium hydroxide, they can react with moisture. Okay, this term pozzolana was originally came from this word pozzolui. It is an Italian word which was used for volcanic ash, which was first used by Romans to make durable concrete. Like if you remember, we had this discussion few weeks ago that how Romans inspired the production of supplementary cementitious material that are presently used. And this pozzolanic reaction, it is a kind of secondary chemical reaction which is happening between silica from pozzolana and lime from cement, which contributes to the strength and the durability. So you can see here in this equation, I have SiO2 which is coming from pozzolana, and I have calcium hydroxide which is coming from my cement hydration. This in presence of water produces CSH, and this CSH is known as secondary CSH. Okay, we generally say it as secondary CSH. Primary CHS is produced by OPC when it reacts with water. Okay. Instead of silica, the alumina that is there in pozzolana, it also reacts with the calcium hydroxide to form calcium aluminate hydrate, which can further contribute to the matrix strength, cement matrix strength. So this is how a pozzolanic reaction occurs when I add SCM to a Portland cement. Okay. Now, based on this understanding of production of SCMs and basics of pozzolanic reaction, try to answer these five questions. And in the meantime, if anyone has any doubt regarding the production part, you can ask. Which answer you are talking about?
Sir, to calculate the gel porosity, assignment number 2,
Okay, so what answers they are mentioning?
57.
You got 57, right?
Yes, yes, sir.
And what they would have given you some answer key, right?
No, incorrect.
Just then try to drop them a mail na, regarding the question that the correct answer is 57, and please give us the solution, because I have also checked the question. The answer should be 57 only. Might they might have incorrectly graded the assignment, or some mistake would be there.
Okay, sir. Thank you.
Any doubt in the discussion till now? If no doubts, just try to answer these five questions quickly.
So in answer key, they have mentioned the range between 45 to 50.
Okay, so that would be incorrect. I guess the problem in the answer would be due to the statement. If you see, they have written at the end of 1 year, assuming maximum hydration. Now, they have not clearly mentioned what is maximum hydration. We are assuming as 100%, but in reality, it does 100% hydration usually does not reach. Okay, hydration in actual condition will be 90 to 95% only after a end of 1 year also. So might be because of that their value is coming out to be a bit lower than 57. But you can still question them. You can ask them for the answer key. You can say that the correct answer is coming out to be 57%, but it is showing incorrect. So please provide us the answer key.
Yes, sir. Thank you. Sir, my one query is there.
Okay.
Sir, after the pozzolanic reaction taking place with the calcium carboxide, hydroxide,
Calcium hydroxide.
so calcium hydroxide. So it will produce the another CHS gel, right, sir? So
Yes.
is it chemically active or inactive gel?
What do you mean by chemically active and inactive?
Means after producing the means when cement is mixed with the water we get this CHH gel, right, sir?
No, like we have
So
only CSH gel is like a single product now. There are no three
uh,
different types of CSH.
so my question is whether it is a chemically active or inactive. That
That
is
is
my
what I'm
question.
asking. Now, what do you mean by active and inactive? Like, what is a chemically active CSH and what is a chemically not active CSH? There is no such classification in CSH. It is
Okay,
the
okay.
final product which
So
is formed upon
yeah,
from the hydration of
yeah,
amorphous silica and
yeah. So
alumina.
can you say the sir CHH gel is the alkaline material?
No, it is not an alkaline material. Now, why it is an alkaline material? It is a
Because
final
when
precipitate. It is a precipitate which is happening now. You
Okay.
can't classify as alkaline or a acidic material. It is a final crystalline product which is forming, you can say.
Okay. Sir, when that cement, when we are going to produce the concrete, no, concrete is basically the alkaline material. So it is having a pH value around about more than 9,
Why
right, sir?
concrete is alkaline? You can tell me the reason. It is because of the
Because,
alkali ions which are there in the pore spaces. It is not because of CSH. See,
okay, okay,
when
okay.
cement, we have Na2O, we have K2O, we have CO, we have a lot of oxides that are there in on OPC. Okay, in Portland cement. When they react with
Okay,
water, we have NaOH, we have KOH, we have COH voltages which are released in the pore spaces between on
okay,
when cement and water reacts. And this alkali materials which are released during the cement hydration, they make concrete alkaline, not the CSH.
okay, 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 okay. Thank you, sir.
Try to answer other questions also now. Okay, let's see the solution. It has been a while now. Okay, so first question, what is the primary environmental benefits of using mineral admixture as pozzolan in concrete? Increases water demand, no. Reduces CO2 emission by replacing Portland cement, yes. Increases the heat of hydration, no. Reduces the workability of fresh concrete, no. So answer will be B. Okay, when we are using, so as we said earlier on slide, I guess slide 16, we said the primary advantage of using mineral admixture is we are replacing a certain part of OPC, and production of OPC requires a lot of energy and it produces a lot of CO2. So if we are replacing OPC, we are reducing the consumption of OPC. So in turn, we are reducing the CO2 emission that is happening during the production of a Portland cement. So primary environmental benefit will be reduction in CO2 emission. Second question, which of the following statements about Pozzolanic reaction is false? It reduces calcium hydroxide content in concrete. It contributes to formation of additional CSH. It increases the permeability. It enhances the long-term strength of concrete. Okay, so generally there is no like in the correct answer should be C in this case. Okay, I will explain you why. See, CH is consumed, that we know, because our reactive silica, it is reacting with the silica from pozzolanic material. They react with calcium hydroxide in the presence of water to form additional CSH. So these 2 points are happening. Okay, it increases the permeability of concrete. No. Why? Because since additional CSH is forming, my pore space that is there inside the concrete, it will not densify. There will be less pore spaces which are available inside the concrete. And since this densification is happening, my permeability of concrete will reduce rather than increasing. During initial stages, it can increase, but if we talk about long-term effect of SCM, it is surely will decrease. Okay, due to addition of SCMs, if the SCMs are added in a correct proportion. Okay. And it enhances the long term strength. Since the additional CSH is forming, the long term strength will be increased. So that is true. Third question, which statement best describes the role of alumina in pozzolanic material? Alumina directly increases the workability. Alumina reacts with calcium hydroxide to form calcium aluminate hydrate, contributing to the synth and sulfate resistance. Alumina inhibits the hydration of pozzolan. Alumina has no significant effect in pozzolanic reaction. So answer will be B. Okay, so we have seen in the previous slide itself that it can also react with calcium hydroxide to form calcium aluminate hydrate, which also contributes the strength and the sulfate resistance ability of my concrete. Okay, so it is not just the reactive silica, it is the reactive alumina also which contributes to the pozzolanic, which has a role in the pozzolanic materials. Okay. Fourth question is silica fume is a natural pozzolan, whether it is true or false. So answer will be false. Why? Because Silica fume, it is an artificial pozzolon. It is a byproduct from a production of silicon metal in electrical arc furnace. Okay, we are not naturally obtaining silica fume, but we are obtaining it as a byproduct from a industry. Okay, natural pozzolans are material which are occurring naturally, like volcanic ash, pumice. These are natural pozzolon. Okay, they possess pozzolanic property and they are naturally occurring materials. Whereas artificial pozzolans like silica fume, fly ash, blast furnace slag, they are industrial byproduct which exhibit pozzolanic behavior when used in concrete. Okay, so that's the difference between a natural pozzolan and an artificial pozzolan. Fifth question: the pozzolanic reaction occurs immediately after mixing water. Mixing after mixing in concrete. True or false? So answer will be again false. Why? Because for pozzolanic reaction to occur, it needs calcium hydroxides that are coming from cement hydration. So it won't occur directly immediately after mixing with concrete. It is a slow secondary reaction that occurs after initial hydration of cement has taken place. So first my cement will react with water and some of the initial hydration, and after some initial hydration period my C3S and C2S will react with water to form CSH and CH. Once my CH is formed by the Portland cement, that CH will react with SCM to form CSH. So it is not happening just after addition of water. It takes time for my OPC to release CH and then my CH will be reacted with SCM. Okay, so it is not an immediate reaction, it takes time. Yes, Rahul, you can ask your question.
I have a question, sir.
Your voice is breaking, so either try check your network or you can drop a message in the chat box.
Sir, we know the pozzolanic reaction consume calcium hydroxide,
Yes,
but we also know calcium hydroxide is responsible for the pH, maintaining the pH of the concrete.
yes.
If we consume calcium hydroxide, then what about the pH of the concrete?
So that is one issue with the pozzolanic reaction or use of SCM. This part we'll see at the end of today's session when we talk about durability of concrete. Okay, so when I will talk about that, you will get to know that though SCMs are contributing in densifying my concrete, they are reducing the pH of my concrete, which affects the corrosion resisting ability of my concrete. So just wait till the end of the session. The answer you will get.
Thank you, sir.
Any doubts in these five questions? Okay, let's move ahead then. Okay, so now before moving into how these mineral admixtures actually affect the concrete properties, like we did in the first session for with Portland cement, it is important to understand why these mineral admixtures are reactive, how they react, and how they differ from one another. So if we are able to answer these three questions, we will have a generalized knowledge that we can use for any other mineral admixture. Okay. So the second question, how they react, we have already discussed. It is the pozzolanic reaction. Okay. For the other two question, we need answer. Okay. So first we'll look at the characteristics of SCMs, in which first we have is the scanning electron microscopic images. Okay. Which is also abbreviated as SCM images. Okay. So as you see, fly ash, it is spherical in nature and it exists in two forms. Okay, we have cyanosphere and we have perlosphere. Okay, so flyish, it is can be a solid particle or a hollow particle. So it can be a solid spherical particle or it can be a hollow spherical particle. So cyanosphere is these are hollow spherical particles. Okay, which are filled up with gases. So you can see here these are hollow particles which are filled with gas inside. Okay, so these are hollow lightweight spheres. Okay, and this is used for making lightweight construction materials. How? So fly ash is used to make lightweight aggregates, which by a process which is known as pelletization and sintering. Okay, so this is one form of fly ash, which is hollow spherical particle. And the second form of fly ash in which fly ash exists is known as perlosphere, which are large sphere containing small fly ash particle within them. So you can see here in this image, there is a large sphere, and inside the large sphere, I have hollow spherical particle within it. Okay, so this type of structure of a fly ash is known as perlosphere. Okay, after fly ash, we have ground granulated blast furnace slag. So unlike fly ash, which is spherical, GGBFS particle is angular and irregular. Okay, and why this is angular and irregular? Because of rapid cooling of molten slag follows by the grinding operation. And this grinding operation makes my spherical particle turn into angular and irregular. Okay, they also have some glassy and amorphous texture, which helps them to contribute to latent hydraulic properties. So, what is this latent hydraulic property? We'll discuss soon. Okay, so for now, you remember ground granulated blast furnace slag has an angular and a irregular shape. Third is silica fume. Okay, so unlike GGBFS and more like fly ash, silica fume consists of ultra fine, nearly perfect spherical particles. Okay, and these are typically 100 times smaller than the cement grain. Okay, you can understand the difference, like both are spherical. Okay, here also there were spherical particle, here also there were spherical particle, but you can understand the difference between the slice of a fly ash and a silica fume based on the scale of these SCM image. Okay, so if you see in fly ash in Sinosphere, the scale is 200 micrometer, whereas in silica fume the scale is 500 nanometer, which is equivalent to zero point 0.5 micrometer. So whatever image you are seeing here, it has a scale of zero point 0.5 micrometer. So if this scale would have been 200 micrometer, they would have been very tiny particles that you would not be able to see clearly. So that small is this is how small silica fume is compared to fly ash. Okay, and due to their nanoscale size, silica fume has a very high surface area, which makes them highly amorphous material. After size, we have green size distribution. Okay, so from the first figure, you can see the mean particle size of different SCMs. So silica fume has a mean particle size of around zero point 0.1 micrometer, whereas blast furnace slag and fly ash, it has a mean particle size of around 40 micrometer and 70 micrometers respectively, and these values are somewhat close to the range of OPC. Okay, while silica fume is comparatively finer than other SCMs and OPC. The same thing you can see in the second figure also, where grain size ratio, we have grain size distribution represented by percentage of weight passing versus particle size distribution. Okay, so compared to sand, you can see OPC is finer, cement is finer. Compared to cement, fly ash is finer, but it lies in a very close proximity to cement, while silica fume is much finer than fly ash and OPC. And if I would plot GGBFS, so it will also come in this range, close to fly ash and in the close proximity of cement. So you can see from the grain size distribution also how silica fume is comparatively finer to other SCMs. So the effect of microstructure and size can be quantified in terms of specific gravity and fineness. Okay, so whatever you have seen now, they are quantified in terms of specific gravity and fineness. So in this table, you can see different materials, their fineness and their specific gravity. So for OPC, my fineness is in this range, 300 to 400, and specific gravity is in this range, 3.1 to 3.15. For Class C and Class F fly ash, my specific gravity can vary from 250 to 600, while my fineness can vary from 250 to 600, while specific gravity for class F fly ash is in the lower range, 2.1 to 2.6, and class C it is in the higher range of 2.6 to 2.8. Ground granulated blast furnace slag, it has a fineness in the range of 400 to 600, since it is uh, ground using milling at the end of operation. It has a it is comparatively finer than OPC and fly ash in general. Okay, and its specific gravity again is in the range of 2.8 to 3. While finally, if you see silica fume, it has a very high surface area, so it is very fine, and its fineness is in the range of 15,000 to 30,000 meters square per kg, which is almost more than 10 times higher than other SCMs and OPC. Okay, and specific gravity is also lower. It is in the range of 2.2 to 2.3. So this higher fineness typically means faster reaction and increased surface area for hydration. That's why silica fume, which is ultra fine, it has a it is strong pozzolanic material. Okay, fly ash, they tend to have a lower specific gravity because of their hollow and spherical nature, especially class F fly ash. While GGVFS, it has a specific gravity in the close range of OPC, which reflects its dense glassy structure. Okay, so this is how we characterize SCMs based on fineness and specific gravity. Finally, in characterization, we have chemical composition. So I will just focus on the major composition, that is silica, alumina, iron, and calcium oxide. Okay. So compared to OPC, you can see GGBFS, it has a higher proportion of silica and calcium oxide. Now, since along with silica there is a higher proportion of CaO in GGBFS, it is observed that GGBFS show latent hydraulic nature. Okay. So it is reported that GGBSs can show latent hydraulic nature. So what do we mean by latent hydraulic? Okay, so it means that it can act as a pozzolan also, but it also shows self-cementing ability under some given condition. So it does not always require CH to produce CSH. Okay, it has a self-cementitious ability also, just like OPC, because of its high calcium oxide content. Okay, in then we have class F fly ash, okay, which has a higher proportion of silica and alumina, while in class C fly ash there is a, compared to class F, there is a lower proportion of silica but a higher proportion of CaO, which again makes class C fly ash a cell cementitious, which again gives class C fly ash cell cementitious behavior. Okay. And finally, there is silica fume, which has more than 90%, or usually more than 96%, 96-97% is say SiO2, which makes them a very strong bosonic material. So this is reactive SiO2. Okay, 96 to 97% reactive SiO2, which makes them a strong pozzolanic material. Now we have answered two questions: how mineral admixtures are reactive and how they differ from one another. But how to judge or how to find out the reactivity of a mineral admixture, like before actually using them in field application. Okay, so to actually to find out the reactivity of mineral admixture, we have two testing methods. So first is pozzolanic activity index. Okay, so what is this? So pozzolanic activity index is, it is the measure of ability of a pozzolanic material to react with the calcium hydroxide in the presence of water. For fly ash, to find the pozzolanic activity index, we use ASTM C618 guideline. Okay, so this guideline tells that initially you need to take a mixture of opposite.
Hello, hello, hello.
Hello. If you have any queries, just wait for the question session to come. Okay. So initially, according to this code, we take a mixture of OPC and the pozzolanic material, which is prepared by replacing 20 to 30% of OPC with my pozzolan, that is fly ash. The prepared spaced sample is then cured for 7 to 20 days under standard condition, and after curing, the strength of my blended cement sample is determined compared to my control sample. So I have two samples. In one sample there is 100% OPC. Okay, so in one sample I have 100% OPC, in the second sample I have suppose 70% OPC and 30% fly ash. So for with both the combination I will prepare cement paste. Okay, I will take a certain proportion of water, suppose zero point 0.4 or zero point 0.5. This much water I will take and I will prepare a cement paste. Okay, now my prepared paste, okay, I will cast them in the form of cubes. Okay, I will cure them for 20 days, and after 20 days I will calculate the compressive strength of this paste of this cube. Okay, so my Pozzolanic activity index, it is nothing but the ratio of compressive strength of my blended cement to the compressive strength of my control. Okay, so a PA value of 75% or higher at 7 days and 28 days indicates good Pozzolanic activity according to ASTM standard. Okay, so this is how this is one of the methods how we can do a Pozzolanic assessment of an SCM. Second is lime reactivity test. So this test measures the rate at which pozzolanic material reacts with calcium
Hello,
hydroxide to
hello,
form cementitious product.
hello.
Uh, who is there? Rahul, if you have any doubt, just write your question in the chat box. Don't unmute and speak in between. Okay, so we were talking about Lime reactivity test. Okay, so this test is performed as per ASTM C 311 or IS 1727 guideline. So what this guideline says, initially we prepare a mixture of lime and pozzolana. Okay, that mixture we prepare with a certain ratio of 1 is to 2m is to 9. This m is the ratio of specific gravity of my pozzolanic material with respect to lime. Okay, the mixture is stored in a controlled temperature and humidity for often for 7 days. Okay, and after curing, the unreacted lime is quantified using chemical titration or thermal analysis. Okay, and the percentage lime that is consumed by the pozzolana is calculated. Okay, so what we do, we have prepared a paste assembly which has lime, CaO, my pozzolanic material, that is my SCM, and my water. Okay, so what will happen if my SCM is showing pozzolanic reaction, it will react with CO in the presence of water to form CSH. Now if it is reacting with CO, it will consume CO, so my CO quantity will decrease. Now, so after a certain age, what I will do, I will determine the unreacted lime. So the lime which is left over, which has not reacted till now, either using chemical titration or using thermal analysis. Thermal analysis we generally do, which is known as thermogravimetric analysis, TGA. Okay, so using these techniques, we can determine how much CO is unreacted, and based on the amount of CO that is unreacted, we can determine the pozzolanic reactivity of the SCM. So higher lime consumption indicates high pozzolanic reactivity, and this rate of reaction also gives an insight into the long-term performance of my pozzolan. Okay, so for different pozzolan, my lime consumption rate can be different, which helps me to judge which pozzolan is strong and which is weak. Now, based on this part, try to answer these four questions first. And now, if you have any doubts, you can ask in this part of discussion. Yes, Rahul, you can write in the chat box what is your question. Others, just try to answer these four questions.
Hello, hello.
Yes, Rahul, you can ask your question.
Sir, I have no problem. I am not that guy.
You have raised your hand. Okay, so who is like who was unmuting his mic? He can ask the question now.
Sir, I am Ashok. I have a problem.
Okay, say. Just write in the chat box. Okay, don't unmute your mic. Okay, so let's see the answers now for these questions. Okay, first question is, which of the following correctly ranks the pozzolanic reactivity of fly ash, uh, slag, and silica fume from lowest to highest at early age of?
Sir, what is admixture?
Who asked the question? Just write in the chat box. Don't unmute and speak. Okay. So for first question, the answer will be uh, B. Okay. Why? So silica fume, it has the highest pozzolanic reactivity. Why? Because of its ultra fine particle size and high surface area. Then I have GGBFS. It is less reactive than silica fume but more reactive than fly ash. Why? Because it shows latent hydraulic properties. Okay, so it has pozzolanic reactive reaction ability also, and it has cell cementitious ability also. Then I have fly ash. In this, I can particularly mention class F fly-ash. Okay, it has the lowest reactivity since it requires additional time to react for OPC to first release CH and then fly ash reacts. Okay, so that's why it has the lowest reactivity compared to other two. Question number 7. The lime reactivity of class F fly ash is typically lower than class C fly ash because, so the answer will be C. Class F flash has a lower calcium content and higher silica content. Okay, so what happens? My class F flash has low is low in silica and rich in low in calcium and rich in silica. So it requires an external activator, that is lime, for pozzolanic reaction. Okay, so now compared to class C flash, it has a lower reactivity. Class C flash has a high calcium content, which makes it more reactive with water and lime. Okay, so in class C, there is cementitious ability also. So that's why my class C flash is more reactive than class F flash. Third question, true or false, GGBFS act as both latent hydraulic material and as a pozzolan depending upon the chemical environment and the curing condition. So this is true. Okay, this we have already discussed. Okay, so GGBFS, it can act as a latent hydraulic material in the presence of water and activators like alkali ions and sulfates. Okay, so if I have alkali ions and sulfate in my system, my GGBFS can react with water directly without need of calcium hydroxide. Okay, and it behaves as a pozzolan. Okay, so when it is combined with the Portland cement, it can react slowly with calcium hydroxide to form CSH gel. So that's why it shows both hydraulic property and pozzolanic property, and it is known as latent hydraulic material. Question number 9. Which of the following factor least affects the pozzolanic reactivity of GGBFS? So the correct answer will be D. Okay. So glass content, so higher glassy phase increases the reactivity. Finer particle reacts faster due to increased surface area. Calcium content, it can influence the hydration kinetics and strength gain. However, CO2 concentration has a minimal effect on the GGBFS reactivity compared to other factors. Okay, so these are the answers for these questions. Now, try to answer these two questions again. Okay, so these are based on SCM imaging. Okay, so based on SCM imaging, try to answer these two questions. Okay, let's see the answers for these two questions so that we can move ahead. So for first question, in SCM imaging, the smooth spherical particles are often observed in fly ash sample are indicative of. So answer will be A. So the smooth spherical particles in of fly ash, it is due to rapid cooling of molten material during the cold combustion. Okay. Question number 11. When analyzing SCMs under SCM, what feature would most likely indicate incomplete combustion of fly ash? Okay, so answer will be B. Okay, so when there is an incomplete combustion of fly ash, it leads to the presence of unburned carbon residues, okay, which appear as irregular porous material in SCM, and this can result in a irregular angular particles with porous surface of fly ash. Okay, so if there is proper combustion, my fly ash will be primarily look like smooth glassy spherical particle. However, if there is an incomplete combustion, it will look like a irregular and angular in nature. Okay. Next we have is hydration reaction of pozzolan. So as we have already seen earlier, a pozzolanic reaction is one where reactive silica and alumina in the pozzolan reacts with the lime in the presence of water to form hydration products. Okay, the same thing is shown here also in the form of equation. Now, what are the benefits of this additional reaction? So there are several benefits of this hydration reaction. First, it is lime consuming. Okay, so it will promote durability. Okay, we have already seen lime is not a desirable product for us in concrete. If my lime is consumed, it can improve us the durability. One negative point is there regarding pH, so that we'll see later on. But in general, since my lime is consumed, it will promote the durability of concrete. It is shows pore refinement. Okay, so since there is additional CSH formation, my pore sizes will reduce, so it will promote durability. It is interface refining, again due to the formation of additional CSH, which increases the strength and durability of concrete. Fourth, it has a slow rate of reaction. Since I need first CH to come from OPC, then it reacts with the reactive silica and alumina. So it is a slow reaction. Okay, so it lowers the heat of hydration. Okay, since it is a slow reaction, it lowers the heat of hydration, and this reaction can be accelerated by alkalis and gypsum. Okay, so this is one additional point. Now we can see in the slide how hydration reaction proceeds in the presence of a mineral admixture. So the microstructure of CSH in cement paste at 7, 28, and 53 days of hydration has been shown for 100% Portland cement and in different proportions of blended cement. Okay, so in these images you can see the microstructure of CSH in different systems. Okay, so in the first case, in case of 100% Portland cement, it can be seen that there is a dense structure of CSH that starts to develop at early hydration point. Okay, and they continue to develop until a dense structure is present at the late time durations also. So you can see from the early ages there is a dense CSH structure that has been developed. Similar structure was observed in 80-20 proportion. So 80% is my OPC and 20% is my SCM. Okay. So in this also you can see there is a similarity in the structure at different ages. Okay. So we can say Portland cement hydration is still dominating even after 20% substitution of my mineral admixture. However, at higher dosages of mineral admixture of 30% and 40%, we can see that there is significant CH. You can see this hexagonal plate like structure. So there is CH, there is significant CH that is present at early hydration ages and also after 20 days hydration. Okay, so you can see in between there is hexagonal plates which indicates the presence of CH, and your structure also compared to these structures you can see these structures are having more porosity compared to earlier structures that we saw. And only after 56 days of hydration we can see that cement microstructure seems very dense and compact. So this shows that hydration of pozzolana is a slow reaction. Okay, it has a slow rate of reaction. Now in this slide we can see the effect of pozzolan on the pore volume and the heat of hydration. So in the first image you can see it represents the pore volume versus pore radius. Okay, so it represents relative pore volume versus pore radius. Okay, for three cases: OPC, OPC plus fly ash plus silica fume, and OPC plus silica fume. So in OPC we can see there is a higher pore volume of coarser pores. So you can see here there is higher volume of coarser pores that which is present. However, where when silica fume is added to the system, we can see both the pore volume and the pore size, they have been reduced. They were reduced. Okay. This shows that pozzolans or mineral admixtures, or we can say SCM, any term you can use, they cause pore refinement due to supplementary cementitious reaction. Now, in heat of hydration, this figure shows how heat of hydration of concrete varies from outside to inside. So, this is my surface, this is my surface, and this is my midpoint of a concrete cube. So, suppose this is my concrete uh, column, or we can say a concrete cube of 100 cross 100. So you can see in the middle and in the top how the temperature changes. Okay, how the temperature gradient look like. So in case of OPC there is a higher gradient between outside and inside. So outside I have a temperature in this value, and inside there is a higher value. Okay, so in outside it is close to 60. However, inside it is close to 75 to 80. Okay, now when GGBFS and fly ash is used, okay, so you can see with the addition of fly ash and slag, you can see there is a uh, reduction in the heat of hydration. Okay, there is a reduction in the thermal gradient between inside and outside. This shows that the reaction rate of with the addition of SCM is slow, which has reduced the heat of hydration, and which has reduced the presence of thermal gradient between inside and outside. Okay, so this is how a pozzolanic reaction being slow in nature reduces the heat of hydration. Now let's see the properties of SCM, effect of SCM on the fresh properties. So here I have clubbed all the three SCMs, fly ash, slag and silica fume, so that we can have a comparative understanding also. So in fresh properties, first we have setting time. So you can see fly ash, it tends to increase the setting time. It delays both initial and final setting. Why? Because it has a slow pozzolanic reactivity compared to Portland cement, which reacts slowly with calcium hydroxide and which delays the hydration process. Okay. Ground granulated blast furnace slag, it can either increase or decrease the setting time depending upon the mixture and the temperature. Why? Because slag is latent hydraulic, which means it can react with the presence of activator. Okay. And which can increase the decrease the setting time. However, in cold conditions, it tends to slow down the setting time also. But in warm condition, it can it may not significantly delay the setting time. Okay. So it depends upon the mixture and the temperature. The availability of activator also affects the setting behavior of my slag. And in case of silica fume, it tends to reduce the setting time. Why? Because it accelerates the, it has a extremely fine particle size and extremely high surface area, which accelerates the hydration process. And since it accelerates the hydration process, it reduces the setting time. Now, in terms of water demand, if I see the effect of mineral admixture in terms of water demand, so fly ash, it decreases the water demand. Why? Because fly ash particles are spherical and smooth in nature, and they act as a tiny ball bearing. So we generally say fly ash shows ball bearing effect. Okay. For fly ash, there is a common term which is known as ball bearing effect. And this ball bearing effect is due to the spherical and smooth near particle nature of fly ash, which improves the workability and flow without requiring any extra additional water. Okay. We have ground granulated blast furnace slag, which can slightly decrease or shows no significant change in water demand. Why? Because my slag particles are angular but slightly finer than cement. Okay, so it shows improvement in packing and reduces water demand slightly. However, this effect is not very pronounced as compared to flash. In ground granulated blast furnace, like there is no significant effect in the water demand. However, in silica fume, there is an increase in water demand. Why? Because of extremely fine particle size of silica fume, which has a higher surface area, which increases the water needed to wet all the particle and maintain the workability. Okay, so maintain the workability, silica fume. If I have added silica fume as a mineral admixture, it will increase the water demand, while fly ash decreases the water demand due to its ball bearing effect. Now, in terms of superplasticizer demand, fly ash reduces the superplasticizer demand. Why? Because of its spherical particle shape. Okay, so this spherical particle shape reduces the water demand, and thus less superplasticizer is needed. For slag, there is a neutral to slight increase in SP demand because its particle size is almost similar to OPC, which results in insignificant difference. Okay, but there can be a slight increase if it has a reactive medium presence, which in which it can show latent hydraulic ability. However, with silica fume, SP demand is increased significantly due to increased water demand due to its fine size particle, which makes more requirement of superplasticizer to maintain workability. Okay, so this is the effect of mineral admixture on the fresh properties. So we have seen how my CSH develops over time. Then we talked about the pore volume. We talked about the temperature gradient from inside and outside, and we talked the effect on setting time and water demand and SP demand. So there are two extreme cases when we talk about mineral admixture: fly ash and silica fume. Fly ash has spherical particle which shows ball bearing effect, whereas silica fume is also has spherical particle but which is very fine and very reactive, so it shows opposite uh, behavior compared to fly ash. Now try to answer these three questions based on the fresh property. Any doubts in this section of the discussion? Sir, please repeat this session of part of hydration of Pozzolon. Which slide? So, like we will see in the end. Okay, just wait for the end. You can ask your questions or something if you want me to repeat. I will repeat at the end. Okay, let's see the answers to these questions now. So, first question here is, in concrete containing both fly ash and slag, which fresh property is most likely to be affected without admixture adjustment? So, the answer will be initial setting time. Why? Because both fly ash and slag, they tend to increase the setting time. Slag, how? If it doesn't have a reactive medium to show hydraulic nature. Okay, so it can also increase the setting time, because this delay in setting time, it occurs because these SCMs, they react slowly compared to Portland cement, which reduces reduces the rate of early hydration. Okay, and since my hydration is delayed, my setting time will be influenced. Okay, it can also influence the workability retention over time, but setting time is more directly impacted. So if I want to select one answer, it will be initial setting time. Question number 13. In a high performance concrete mixture containing both fly ash and silica fume, which of the following is the most which of the following is the most likely to affect workability within the first 30 minutes? So answer will be B for this question. So why? Because silica fume is highly reactive and it has a very high surface area, which means it quickly absorbs water. However, there is flocculation that can also occur, which significantly reduces the workability within minutes. Okay, which can't be properly controlled by the super plasticizer. Because of such high reactivity, there can be flocculation of my final products, which can occur. Okay, so that's why the answer will be B. Okay, so most likely effect on workability is due to the accelerated water absorption by the unreacted silica fume and for flocculation. For question number 14, in cold weather question number 14, in cold weather concreting, the use of class C fly ash is more advantageous than class F fly ash due to. So the answer will be in this case, because class C fly ash shows self-cementitious property which accelerates the early hydration and strength gain. So this we have already discussed. In class C fly ash, there is a higher proportion of calcium oxide, which shows self-cementing property. Like it can react with water independently to contribute to the early strength gain. Okay, and this makes it beneficial in cold weather, where early strength development can be crucial to avoid any freezing damage. Okay, so answer first with C, then B, and then B. Okay. So I request don't unmute and speak in between. Okay, if there is noise coming from your background, so just keep yourself on mute. Now the last segment is the effect of SCM on the hardened properties. So mainly here we'll talk about the compressive strength, because all other properties like tensile strength, modulus of elasticity, they are directly influenced by the compressive strength. So in the first figure, we can see the strength development of OPC and OPC plus fly ash based concrete with time. So at early ages, you can see fly ash shows a slower strength gain up till 28 days. Okay, at 28 days, it has a almost similar strength compared to OPC, and beyond 28 days, it shows a higher strength than OPC. Okay, so like in OPC concrete, beyond 28 days, strength gain is not much. Okay, you have reached the stable state. However, in fly ash based concrete, there is a still significant strength gain occurring due to secondary hydration reaction. And this is evident from the CH content, consumption of CH content in concrete over time. So you can see in fly ash added concrete, the CH content is lower than OPC based concrete. Okay, up till 28 days, you can see the CH content is increasing. However, beyond 28 days, it starts to decrease as CH is consumed by fly ash to form CSH. Okay, so that's why my CH content is reducing. Okay, my CH content is reducing in case of OPC plus fly ash system. So in this slide also you can see the strength gain pattern of different concrete batches after different hydration issues. So we have four different types of concrete. We have OPC 100%, we have 25% replacement of OPC with fly ash, we have 40% replacement of OPC with slag, and we have 8% replacement of OPC with silica fume. So how these values came? So these are optimum replacement level for fly ash, slag, and silica fume. So it is not like you can replace any OPC by any proportion of fly ash like 50, 20, 30. There's a limit till which a replacement of OPC will be beneficial. Beyond that limit, it won't be beneficial. Why? Because CH that is produced from OPC is actually getting consumed by my HCM. Okay, so if there is not enough CH produced by OPC, then the remaining SCM is of no use. Okay, so that's why we need to have a balance between how much CH my OPC can is producing and how much CH my SCM is consuming. Okay, so for that there are different like optimum dosage for different SCM. Okay, so in this slide you can see at early age, you can see silica fume has a higher strength compared to OPC. However, slag and fly ash had lower strength compared to OPC. Okay, at 28 days, almost similar strength is there in OPC, slag, and fly ash system, while silica fume showed a higher strength compared to them. However, after 90 days of hydration, fly ash and slag system, they showed a higher strength compared to my OPC and comparable strength compared to silica fume. So it shows that slag and fly ash, they react slowly, but they will gain strength over time. Okay, and compared to OPC, all the three SCM system, they showed a slightly higher strength value. So in this slide, we have concrete resistivity data. Okay, like compressive strength, resistivity of concrete is also an important property which is directly related to the densification of concrete microstructure. So a higher resistivity value implies more. There is a lower ionic conduct through concrete, which implies that there is lower permeability of concrete. Okay, and hence better performance of concrete in long run. So in first figure, we can see the resistivity data of three OPC based batches with different W by C ratio. So this is 0.3 W by C ratio, this is 0.4 W by C ratio, and this is 0.5 W by C ratio. Okay, so you can see when as with more water presence, my resistivity value decreases. Okay, because there is more higher porosity in my concrete. So we know compressive strength and water to cement ratio has an inverse relationship. Okay, so as I increase the water content, the compressive strength also decreases due to the higher proportion of capillary water or capillary pores which are present, which also decreases the bulk resistivity. Okay, and in the second figure, you can see bulk resistivity for different batches. First is OPC, second is OPC with fly ash, and third is OPC with slag. So you can see with age, SCMs they show a higher bulk resistivity compared to OPC. So you can see here is my OPC after 90 days. However, my slag and fly ash added batch, they had a higher bulk resistivity due to pore densification which is happening because of secondary CSH formation. After mechanical properties, we have durability properties, in which first we have it is the effect of a mineral admixture on drying, shrinkage, and creep. Okay, so drying, what is drying shrinkage? It refers to the reduction in volume of hardened concrete when it loses moisture over time. Okay, whereas creep is the time dependent deformation of concrete under sustained load. So if the load remains constant, concrete will continue to deform slowly, and this property of deformation of concrete under loading is known as creep. Okay, so what is the effect of SCM on these two properties? So fly ash and slag, they reduce the drying shrinkage since they create a dense microstructure. However, silica fume can increase the drying shrinkage. Why? Because of Mainly because of autonomous shrinkage. Who is this who is speaking in between? Can anyone tell me? Please keep your mic on mute. Don't disturb in between if you have no query. Um, I will I will remove you from the call right now since you are creating a lot of issues in between. Okay, so we have seen here first on drying shrinkage. Okay, silica fume, it increases the drying shrinkage. Why? Because of autonomous shrinkage. What is autonomous shrinkage? Shrinkage due to internal chemical reaction that happens and due to rapid reaction rate. Okay, so silica based concrete, they need proper curing so that curing, they need proper curing so that there is no drying shrinkage. In terms of creep behavior, my fly ash and slag based concrete, they have similar property. Okay, they have a higher creep behavior at early age, but it reduces at in long term due to improved microstructure and strength gain. However, silica fume, it generally reduces the creep because of its increased compressive strength at early age, which creates a stiff microstructure. So more denser is my concrete, lower will be my creep behavior. Okay, and more rapid is my hydration process, higher is the chance of drying shrinkage to occur. Okay, so shrinkage can be of different types. So in silica fume, there is autogeneous shrinkage that becomes an issue because of its increased reactivity. So in this slide, we can see the change in creep value. Okay. So in first figure, we have OPC and OPC plus fly ash added batches. So you can see a different percentage of stresses like 60%, 80%, and 30%. Fly ash added batch, they showed a lower creep value after prolonged exposure. Okay, compared to OPC batch because of its dense microstructure. In the second figure, you can see the similar observation was made for slag batch. Okay, so with increased percentage replacement of OPC with GGBFS, the creep value was found to continuously decrease under loading. Next, we have
सर कुछ समझ नहीं आ रहा है.
क्या नहीं समझ आ रहा, who is this? Can you wait till the end of the session and write your queries in the chat box? Okay, so these all things have been picked from the live session. So there is nothing new which is coming here. So if you are not able to understand that, it means that you have not went through the session properly and you are not regularly following the course. So the last section is the effect of mineral admixture on the durability properties. Now, when we talk about durability property, this section of durability we'll talk later on also, but for now I will just give you a short small recap, like small overview of what is durability. So see, in field application, the concrete that we use is reinforced concrete. Okay, so in reinforced concrete there are steel reinforcement that is embedded inside a concrete cover. Okay, the cover can be of thickness 25 mm, 50 mm, 75 mm based on the need. Okay, now why we are providing steel reinforcement inside concrete? Because concrete is weak in tension, so steel provides the tensile strength to concrete. Okay, now this system of reinforced concrete, they were supposed to be inevitable, like something which has a very high lifespan which won't collapse in any case. Okay, however, In aggressive environment mediums, like when this reinforced concrete is subjected to some aggressive environment, what happens? The reinforced concrete, they degrade over time. Okay, and this gives rise to durability properties, durability issues. Again, I will remove you from call. Okay, so when my reinforced concrete it is subjected to some adverse environment, what happens? My durability of concrete is hampered, and that's why durability properties have been taken into consideration to check the quality of concrete. Okay, so by durability I mean ability of a concrete to resist weathering action. Okay, now this durability issue of reinforced concrete is mainly due to the corrosion of embedded reinforcement. And how this happens? The aggressive ions which are responsible for corrosions are chloride ions and CO2. Okay, so when these
हाँ हाँ
ions
ठीक है जी
penetrate through
सर क्लास कब
concrete,
खत्म होगा
if you don't want to attend, you can leave now also. Okay, so these ions, these are what is causing durability issues to concrete. Okay, so these ions they penetrate through the concrete cover and they reach the steel reinforcement. So like this is my reinforcement and this is my cover. Okay, so they are these ions they penetrate through the cover, they reach the steel reinforcement and they cause corrosion, which becomes a durability issue for my concrete. Okay, now how this happens, on what things they depend upon, this we will see later on when we'll talk about durability. But for now, you just remember we are talking about reinforced concrete when we are talking about durability. Okay, so now we know there are two ions which are critical for us, chloride and CO2. Okay, so the rate at which my chloride ions will move through concrete is what is represented as chloride ion diffusion coefficient. Okay, so this concrete cover, okay, the rate at which my chloride ions will move through my concrete, it will determine the durability of concrete. So if they are moving faster through the concrete, they are more degrading my concrete more. If they are moving slower through the concrete, they are degrading my concrete less. Okay, so with SCM what happens? My concrete is becoming dense, so my rate of chloride ion movement will become slow, so my diffusion coefficient value will lower. Okay, so this is the effect of SCM on a concrete durability. So you can see here in the first image, you can see after at different depths. Okay, so I have 5 mm depth, 10 mm depth, 25 mm depth, up till suppose 75 mm depth. Okay, so at different depth you can see how much chlorides are there in concrete. Okay, so based on these profile that we get, we can determine the diffusion coefficient. Okay, and this figure shows the diffusion coefficient value. So you can see compared to OPC, at initial age, my slag has a very low
हेलो सर
diffusion coefficient value, which means it is more dense. Concrete is more dense. Yes. Who is speaking here?
हाँ सर बोल रहा हूँ ये कि आपके घर में क्या हुआ है आज खाने में
Please don't disturb in between. Na? If you don't want to attend, you can leave the class. I will report about you in the NPTEL session next time, so they will take care of you. Okay, so this is how my SCM, they are densifying the concrete and they are reducing the diffusion coefficient of chlorides. However, like initially someone mentioned that since the calcium
आई
hydroxide
एम
is
बैक
consumed, so I guess I've spotted who is the one. I request not to disturb in between classes. Like others are attending the class seriously, so please be serious while attending the class. Okay, now, like earlier, someone said that since CH is getting consumed, my concrete will become less alkaline, so it can affect the properties. So that is where carbonation induced corrosion comes into action. So what is carbonation? Okay, so in carbonation, what happens? It is not directly affecting the steel. So the CO2, it is not directly reacting with steel. But what happens? This CO2, it reacts with calcium hydroxide that is there in my concrete to form CaCO3. Okay. Now, since my calcium hydroxide is getting consumed, my pH of concrete decreases and my steel corrosion rate increases. Okay. This we'll see later on how it happens. Okay. So since pH decrease, what happens? There is a stable passive layer which is there on the steel surface which breaks down and which increases the corrosion rate. So lower is the pH, higher is the rate of corrosion. Okay. Now SCM has a negative effect on carbonation. Why? Because SCMs, that they are consuming CH initially and forming CSH. So there is less CH that is available to react with CO2, and thus CO2 can penetrate to a greater depth compared to a concrete where there was just OPC. So in this way, SCM can have a negative effect on carbonation. Okay, and this is what it is represented in this table also. So for carbonation, we generally use this equation. X is the carbonation depth, the depth till which CO2 has reached. K is the carbonation rate, and T is the time. Okay, so you can see this value of K. So compared to OPC, we have a higher value of K when we use SCMs. This shows that since CH is consumed, there is nothing to block CO2. So it is reaching to a greater depth. Okay, so they increase the rate of carbonation when SCMs are added. So in terms of chloride corrosion, SCMs have a positive effect. However, in terms of carbonation induced corrosion, SCMs can have a negative effect. Now try to answer these questions like based on the final part of discussion, and if you have any queries in the final part, you can ask now. Yes, you can ask your question.
Good evening, sir.
Yes.
Sir, I'm Sabrishwaran. This is not regarding the final part, but it's a general doubt I have.
Okay, can you wait for like 5 minutes? We will just end the
Yeah,
session
yeah, okay,
from
sir.
after these few questions, and then we'll
Okay,
talk about any general doubt. Just try to
okay,
answer these questions right now.
okay, sir.
Guys, can you leave the class? Class is over.
Yes, in the start of the class, Anand, in the start of this session, I have told you that the correct answer will be around 57.17. Okay, but they have given the answer 45 to 50. So you just try to contact with the NPTEL team. Na? Just ask them for the solution. Tell them that the correct answer is coming out in this range, and you have marked it as incorrect. They will tell you the solution. Email ID, like you usually get a mail na from NPTEL team for live session. So just using that same mail ID, try to contact them because I also don't know the exact mail ID.
Okay, sir. Thank you. Means the answer is your answer is also coming up to 57.16, no?
Yes, sir. Yes, yes.
Okay, thank you, sir. Actually, I saw that, so I was confused. You
Just
how?
try to contact them. Maybe they have made a mistake in the making the answer key, you can ask them to correct it, or
Okay, sir.
ask
Thank
them for
you.
the explanation why they are getting an answer from 40 to 45 to 50.
Yes, yes, exactly, sir. Online, I think I just made the online. Just a minute.
Just wait now,
On,
just let this discussion end, then we'll talk, so that
okay, sir.
others can
Thank you.
solve the questions.
Thank you, sir. Okay.
Okay, let's see the answer for these three questions now. First, at what percentage replacement of cement is fly ash generally considered to optimize both strength and workability? So, the answer is 15 to 25%. Okay, so as I have told earlier, up till a certain replacement percent only, a SCM will show its positive effect, because a certain amount of CH should be released from OPC for SCM to react. If you have a higher proportion of SCM, maybe there is not much CH that is available for SCM to react, so SCM won't show any effect. Okay, so for fly ash, the optimum replacement percent, it comes out in the range of 15 to 25. Which of the following statement about the use of SCM in concrete is false? SCM always improve the early strength. So this is not true. It doesn't always improve the early strength. Okay. So we have seen in case of fly ash and slag, it tends to reduce the early strength. So if you remember this uh, diagram here, figure, you can see with the addition of fly ash and slag, there was a reduction in early strength. Why? Because of its slow pozzolanic reaction. Okay, so it requires OPC to release CH first, and then it reacts with CH to form CSH. So it is not always that it will increase the early strength of concrete. Silica fume can increase the early strength, but not fly ash and slag. Not always they increase the early strength. They can improve the long term strength and durability. Third question, which of the following SCM combination would likely result in the best balance of early strength and long term strength? So my answer can be moderate slag plus low silica fume. Why? Because my slag at moderate level, it will improve the long term strength. However, it will still allow reasonable early strength, while silica fume will have an enhanced early strength. So I will have a good fit between early strength and long strength. Other answers like uh, high flash with low silica fume can also be correct. Okay, or this option like high flash and high slag, this is incorrect. Why? Because it will delay the strength gain initially, so it won't be correct. Low flash and high silica fume, again, since there is low flash, there won't be a so like who was this? I'm encountering a lot of disturbance in between this session. Okay, so this option won't be correct since there's low fly ash. So long term strength won't be like it won't give me the best balance between long term and early age strength. So correct answer is B in this case. Now just try to answer these last three questions. So these are like questions which are apart from what we have discussed in the session. So additional content you can say. Okay, because there are a lot of things that can be covered, but it is not possible to cover in a 2 hour session. So I've represented that in 20 minutes. Rudra, please don't disturb in between, else from next time you won't be allowed to join the session. So as I was saying, these questions are like additional to what content we have discussed. So they will help you to like build up on more possible questions that can be asked or that can be related to the mineral admixture discussion. So you may not know all the answers here, but try to think what can be the solution. I am unmuting right now, everyone, so that there is no disturbance in between. We will later on. I will allow you to mute, unmute, and speak. Muting. I am muting right now, everyone. Okay, let's see the answer for these three questions, the final three questions, so that we can move to the discussion part then. Okay, so first question is the chloride binding capacity of SCM. So firstly, what is known as chloride binding? So what happens in concrete when chloride ions enter na? So these chlorides, they can react with aluminates and they can form some product. So these products are known as Friedel's salts. Okay, so this is known as chloride binding. Okay, this is not we have discussed now. This is a part of durability discussion. But for now, remember the chloride binding capacity of SCM is influenced by the formation of Friedel-Stalt in the presence of aluminates. Okay, so this is an additional advantage of addition of SCMs. Like slag based SCM, which has higher aluminate content, they show higher chloride binding capacity. So instead of allowing chlorides to freely move to concrete, it binds the chloride and blocks its movement. The carbonation rate of concrete is inversely proportional to which of the following properties significantly influenced by SCM. So the answer will be the amount of free CaOH whole twice and tortuosity. So tortuosity is a term which is used for permeability. So it is inverse of permeability. How random is my pore connectivity? That is known as pore tortuosity. So carbonation rate is inversely proportional to the amount of free CaOH whole twice. So in case of SCM, my free CaOH whole twice is less, so my carbonation rate is more. Okay. Degree of hydration of concrete with SCMs is critical for durability. Yes. Which of the following condition best promotes the hydration of GGBFS in concrete? So if we will have a high curing temperature and prolonged moist curing, then my degree of hydration of a slag based concrete will be improved. Okay. So high curing temperature, what it does, it accelerates the reaction. Okay, in moist curing ensures that there is enough water available for hydration. Okay, so if these two conditions are there, we can improve the, we can promote the hydration of a slag based concrete. Any doubts in these three questions? So this was all for today's session where we discussed about mineral admixtures. Okay, thank you. Now you can ask